Alright, a few days ago, a friend sent me a proof that he was doing in his linear algebra class, and I just thought it was so clean and so cool. It's not like a crazily super known theorem, but it's a really cool linear algebra proof. So for anyone that likes linear algebra or that actually has to learn this, this is a pretty cool video. It's really clean how we actually get to the proof, and the actual statement is if p minus one AP equals a. So basically, this is usually the change of basis matrix. We usually have like a matrix A, and then if we multiply it by p minus one times p, this will equal, let's say, b. So we change the matrix of A into b. So b and A are still the same matrix. They still represent the same linear transformation, but b is in a new matrix. It's now in the matrix of the basis vectors of the new matrix are encoded in p. But basically, if we have a matrix which is the same, like let's say we change the basis of a matrix, and at the end we get the exact same matrix, so the coefficients are exactly the same. So if our matrix isn't changed for any invertible matrix B, then it has to be a diagonal matrix with all the diagonal entries being the same. So it can be any, A is any scalar in the field, and the matrix A, if this property, if it is to hold for every invertible matrix B, and its inverse, so it has to be invertible, then A has to be diagonal matrix with all diagonal terms. How do we actually prove this? Like it's a, I guess it's a solid theorem, but the actual proof is very, I don't know, it's just really cool. It's not very hard linear algebra, but it's just very cool how we do it. So first of all, I'm gonna write down again the p minus one AP equals A. So and now an important thing about matrix multiplication is it's not commutative. If you have A times B, this is generally not the same thing as B times A. It's completely different because again, with matrix multiplication, like with how it's defined, you don't usually get the same result if you have this. So what we're gonna do now, first of all, is A multiply A by P on the left. So I'm gonna have PA. So I just multiplied A by P. A equals this. So then I can also multiply this on the left by P. So I get P times P minus 1 AP. That was our original thing. Now what we can see is P times P minus 1. Well, that's just a matrix times its inverse. That always just equals the identity matrix I. And any matrix I, any matrix times its identity just equals the matrix again. The identity matrix, for anyone in case they don't know, it's it's just the diagonal matrix, but with all the terms, A being 1. So it's a matrix with all ones on its diagonal, and everything else are just zeros. So this is this I, we can just get rid of this I, and what we're going to be left with is PA equals AP. Oh my goodness, so what did we just find? If this property is to hold, so if this property is true, then this also just has to be true. By multiplying it by P here, we get this over here, which means that if A, if P minus 1 AP equals A for every invertible P, so if A, is if it's a matrix that is unchanged by any change of basis, then it has to be such a matrix that it commutes with every single invertible matrix. So PA has to equal AP. So for any R matrix A, if this holds, has to be such that it commutes with every single invertible matrix P. Then this is a pretty cool property. So this these two things are saying the same thing. So what we're going to be trying to do for the proof is actually use this property to find out how A looks like. Now, what we're going to do now, and this is the coolest thing, because all we have is this information. We have information that we have a matrix A, and this matrix, we got to find out how it has to look like, such that it it commutes with every single matrix that exists, with every single matrix P that is invertible. So how do we squeeze information out of A? How do we actually know how A is going to look like? Well, we're going to construct a very specific invertible matrix. We're going to construct a specific invertible matrix, and then we're going to use the fact that this has to be true, and we're going to get information out of A just by using this property and using a very specific invertible matrix. It's going to be really cool. So what we're going to do is, for every I that doesn't equal J, we're going to define a matrix EIJ. So I'm just going to define it like this, and EIJ is just a matrix which is 0 everywhere. So if I make it like a 4x4 matrix, it's 0 everywhere except for the ijth column. So let's say in the ijth column, in the ijth index, it has a 1. So let's say if I make a matrix with zeros everywhere, and then if I say that this is row I and column J, only so if for example this matrix over here would be E, I in this case is 2 and J is 3, so E2 3. So it's a 4x4 matrix, and I am saying it's a 4x4 matrix, so it's 0 everywhere. The only place where it's not 0 is in the in the 2 3 index, so second row, third column. This is how we define EIJ. So 0 everywhere except 1 in the ijth index. And now what I'm gonna do now, because this matrix obviously isn't invertible, what I'm gonna do now is I'm gonna call our I'm gonna just keep this just so we remember. So I'm gonna have like a random one here, then everything else is zeros. I, J. So I'm gonna highlight it. This is the ith row in jth column. So what we're gonna do now is our matrix, our invertible matrix P is gonna be the identity matrix IN. So just diagonals with ones everywhere plus EIJ. This is gonna be our invertible matrix. First of all, is this an invertible matrix? How this is gonna look like, this Pij. Well, this is literally just gonna be the identity matrix I. So it's gonna have ones everywhere on its diagonals, and then zeros everywhere else except for the ij term. And again, you see I cannot equal j, so we won't have a 1 here because it'll be the same thing. For a random ij term, we're gonna get so there's gonna be zeros everywhere except there's gonna be a random one somewhere, like randomly in the ith row and jth column in this index there's gonna be a 1. So it's gonna look like the identity matrix and a 1 somewhere randomly. Now why is this invertible? Well, first of all, notice that Eij squared will always equal 0. And this is just by the property of matrix multiplication, with how it's defined. I guess we could also prove this, but I'm just going to do a little example with, for example, a 2 by 2 matrix. So I get 0, 1, 0, 0. This is our Eij matrix where, where I would be 1 and j would be 2. And again, if I say it's squared, that just means I multiply with itself. And again, there should be a 0 here. And again, now, how I do this, this is just 0 times 0, so the first term will be 0. So the first term will be 0, and then I multiply these two terms, this by this and this. This is also 0, and then and then I multiply 1 by this and by this, so this is also 0, and then for the last term it's going to be 1 times 0, and again 0 times 0. So it's 0 everywhere. Matrix multiplication is defined in such a way that if your ones are not on the diagonal term, you will never have this term times this term. They will never multiply with each other. They will always multiply by something else, and everything else is 0, so this will always be 0. So Eij squared will always be 0. That's just how matrix multiplication is defined. And now what I can do with this fact known is I can have our matrix P, which is In plus Eij, and I can multiply it by another matrix In minus Eij. Again, this is our matrix P, and this is some other matrix. So literally this matrix here looks like that. It looks like a matrix. Let's say if I make a 2 by 2 matrix, it has ones everywhere in the diagonal, and then somewhere randomly, let's say here it also has like a 1. And then this matrix will be the exact same one, but there's a negative one in the place. It's minus Eij, so we're gonna have a negative symbol here. And if I multiply this out, well, what do I get? I multiply everything. If I actually multiply this together, I get In, because we got In times In. Obviously that's In. Then I get minus Eij. Then I get multiply this by this. I get plus Eij, and then I'm kind of running out of space here. Oh my goodness, why didn't this copy? And then I move this down. The last thing is Eij times negative Eij, so it's negative Eij squared. Well, negative Eij and plus Eij, that just cancels, and Eij squared we said equals 0. So what we're going to be left with is In. If you do the classic foil multiplication with this. So basically, if we multiply P, our matrix P, by this other matrix, we're going to get the identity matrix. Well, that means that this can be nothing else but the inverse of P. If you have any matrix, A, and you multiply it by a different matrix, let's say, B, and you'll get the identity, well, then B has to be the inverse of A. That is just, a rule in linear algebra. So we just found out that P is invertible because there exists a matrix, there exists this matrix, which if you multiply by P, for any Eij, you're going to get the identity matrix, which means P has an inverse. So now we know that P is invertible. Bang. And now with this fact, because P is invertible, we can use this fact to, we have PA equals AP, and since P is invertible and P is this, we can write P instead of P, we can write this over here. So we get In plus Eij times A equals A times In plus Eij. This is just our matrix P. And again, if I multiply everything out, I get A plus Eij. Here order matters. Here A is multiplied on the right, and here A is multiplied on the left, so I get A plus A Eij. The A's obviously cancel, and I get that Eija equals Aeij. This is our divine kind of our divine relationship. This is really important. This is kind of like a very important thing. And now we're going to finish this proof with this statement over here. This statement will give us so much information. So this is what we found. Again, I'm just specifying this again. A commutes with any invertible matrix P. We just found a specific matrix P, which is shaped like this. And because A commutes with it, we can say this, and so we can get this out of our so we can get this statement. If our initial hypothesis is true, so if we're saying that we're saying that this is true, then and if we find this specific P, it also has to be true for that specific P, and then we get this result over here. So basically, this is a matrix with zeros everywhere except the one somewhere. This will literally be a matrix with zeros, like this. I can make it a bit bigger, but this would be a matrix with zeros everywhere except the one somewhere, and times our matrix A, and then again our matrix A times this same matrix, and this has to be the same. Now let's go step by step, and let's actually see what this reveals to us. So first of all, wait, let me just go to my notes over here. So first of all, let's focus on this over here. So let's focus on Eija. Well, let's look at every element of Eija to actually see how this looks. So Eija, the kth element, this is just how you write any element of a matrix. So this will be row k and then and column L. Well, this just equals to the sum from m equals 1 to n of Eij km times AML. And again, this, here I'm just writing, this is the kmth term, this is the kmth term of our matrix, Eij. And I'm just copying down as the matrix Eij because, it's kind of useful to keep it like this. And here I'm using, not a capital A, but a small a because, this is just a term of A, or, we have a matrix A, and this matrix A has, a bunch of the coefficients. You have A11, A21, A31, A21, A22, A32. This is our matrix A. So when I'm saying AML, I'm just saying one coefficient of A, or one value of A. And this is how matrix multiplication is defined. When you multiply one value by another one, if you want to look at what the kth element of this multiplication will be, of what this product will be, well, the kth element is the sum when m goes from 1 to n. If these are m by n, if these are m by n matrices of E of the kmth term times the mlth term, and I sum this together. So this is how matrix multiplication is defined. I mean, it's a bit confusing. The best way is to draw this out, but basically what we're gonna find is that Eij, this equals 0. This matrix equals 0 for every, this matrix is 0 for every term except for the ij term. So for every k that isn't equal to I, we're going to get that, this will be 0. And also for every m that won't equal to j, this will be 0. And what does this actually tell us? Well, this tells us that this matrix, when k, our result will be 0 for every row except for the ith row, except when k equals I, this won't be 0. So, so A will actually remain. And so only the ith row of our kind of result won't be 0, and also m will have to equal j, so only the jth term, so only the j only the parts of it, only the jth row of A will actually get copied over. Every other row won't get copied over because it's going to equal to 0. And now this is really, really confusing when you try to explain it. The best way is to just draw a diagram and draw out the actual matrix multiplication and see what happens. So let's imagine we have a 3x3 matrix, 0, 0, 0, 0, 0, 1, 0, 0, 0. This is our Eij matrix, and in this case we have a 1 here, so this is j, so in this case I would be 2 and j would be 3. So this would be E2, 3, and a 3x3 matrix. And then we multiply it by our matrix A, and our matrix A, just has its own terms. It has the term A11, A12, A13, then it has A21, A22, A23, and then it has A31, A32, A33. So this is just a 3x3 example, and if I multiply this together, let's see what I actually get. Well, first of all, I multiply all these coefficients with these coefficients, so it's a11 times this plus a21 times this plus a31 times this, and obviously that will be our first term, and that is going to be 0. Because it's all multiplied with 0. This is what the sum is exactly saying. Then for our second term, this is for our I term. So this is for a 1 term when k and l would both be equal to 1. And then let's say if we're trying to look for this term over here, we'd multiply this by this over here. So again, we'd multiply all these terms. Or if we want to do the bottom columns first, now we multiply this by this over here. And what we get is, again, a11 times 0, well, that's going to be 0, plus a21 times this, that's going to be 0, plus a31 times 1. Well, oh my goodness, a31 is going to get copied over. Our sum, here in this case, in our sum, only a31 is going to survive. And wait, let me actually delete these dots. But yeah, this is 0, and this is a31. So for the index 2, 1, when k is 2 and l is 1, only a31 is going to survive, and everything else is going to be gone. Because again, k, only when m equals j and k equals I, this term will survive. We can see this with the matrix multiplication. And again, when I do this times this, when I multiply them, it's all going to be 0. And now, now I shift to this term over here. Now it's going to be this times this, and we can see, the sum of that's always going to be 0. Then I have this times this, and again, this will be 0, this will be 0, but a32 times 1, that will remain. So we're going to get a32 over here, and then everything else, again, let me get rid of these things over here to keep it clean. So we're going to copy over a32 because it's going to survive, and then again here we're going to get zeros, and then we do it for the last case. So we do this times this, and again it's going to be 0, and in this case a33 is going to survive, so we get a33, and then for the last case, this times this is always going to be 0. So this is our result. This is what we're going to get. And now what we can see is what happens is that we basically what happens is that this this operation over here, if we multiply a by the ijth matrix, so if we do I have it here, eij times a, what is going to happen is that we're gonna take the jth row of a and put it in the ith row of a result. So we're taking the jth row of a. So here j, in this case, the 1 is in the index ij. In this case, j is 3. So because 1, 2, 3. In this case, j equals 3. So we're taking the jth row of a, so the third row of a, and we're putting it into the ith row of a result. And in this case, I is 2. We get 1, 2 equals I3. So in this case, I is 2. So we're taking the jth row, the third row of our matrix A, and we're pasting it into the ith row of our result. This is exactly what's happening here. Like this, when we have this, when we have a, so if we have a matrix, let's say E5, 4, A, these are both, let's say, whatever, 6 times 6 matrices or whatever. Like, what's going to happen is we're going to take the, so it takes the ith row, so we're going to take the fifth row of A, and we're going to put it into the fourth row of a result, and everything else will be 0. So that's exactly what happens. So this is kind of the intuition here, and again, you can do it. You can go through the indices and actually explain it to yourself that this will always be 0. Like for example, if L won't equal to M, then this will always be 0. So all these A's will be 0 only when only when M will be equal to J. So only the jth row of A, then this term will be 1. So this term is going to remain, and we'll do this for every case. So for every column of the jth row. But the geometric intuition is way cleaner. If you just show it like this. And then again, now for the other one, I've been explaining this for a bit too long. Now we have A, E, I, J, and we're going to look at A, E, I, J, K, L. And now what that is going to be, that's just going to be the sum as m equals 1 to n of A, K, M times, E, I, J, M, L. And again, the easiest thing is just to do the example again. You can go, step by step, and you're basically going to see that only the ith column of A will be considered. Is considered. Only ith column of A is considered, and again, why? Because only the ith column of A is considered, because m has to equal I. If m does not equal I, then let's then this index, for any L, if L is anything, between 1 to n, if m does not equal I, we're gonna get, let's say, we won't get, this index ij. This is only one for ij, so m has to equal I, so we even get a possibility, m has to equal I and L has to equal j. Both of these have to be true for eij to equal for it to not be 0. So m will have to be I. So this will have to be I. So we're only, the only time this coefficient is going to survive is when m will be I. So in the ith row of A. And the only time it will also survive is, for the only case that this will survive is also when L equals, when L equals j. So only the ith column of A, it will be considered, and it's gonna paste it only into the jth row of Aij. So only jth column of AE will be non-zero. And again, why will only the jth column of A be non-zero? Again, because L will have to be equal to J for this index not to be 0. And when L equals J, well, L will have to be J. So only the only time this will be non-zero is when L will be equal to J. So only the jth column of this will be non-zero. And when we actually go over this again, if I want to do the example, we have our matrix A. So our matrix A will just be A11, A12, A13, A21, A22, A23, A31, A32, A33, and then bang, and then we times it again by, let's say, the same type of matrix, which has the one in this column over here. Everything else is zeros, and what we get again, we multiply this by this. We obviously get zeros everywhere. Then we multiply this by this, and this by this. Again, we clearly get zeros everywhere. Bang, bang. Then we multiply this by this. Again, we get zeros everywhere, and we get zeros everywhere always again. And then we multiply this by this, and we see the only non-zero thing will be when 1 is multiplied by A12. So we're going to get A12 over here. And again, then we multiply this by this, and the only time this will be non-zero is for A22. And then for the last case, again, 0 times this will be 0. 1 times this, A32 will survive, and A33 will be gone. So A32 is going to survive. That is all that is going to remain. So what happens again now is that we take, well, what happens in this case is that we put the ith column of A. Again, we said that only the ith column of A will survive. So we put the ith column of A into the jth column of our product A, E, I, J. So again, and we see in this case I was here. This is the row and this is the column. So in this case I is 2. So we take I is 2. So this is the second column. So we take the second column and we put it into the jth column. Here in this case J is 3. So we put it into the third column. So we take, in this case, I is 2, J is 3. So if we look at the second column of our matrix A, it will be put into the jth column. In this case, our index J is 3, so it's going to be put into the third column. This is what's going to happen. This is kind of one of the hardest things to get. And now, after we understand this, again, we know that EIJ, this is kind of the, this is the craziest part of the proof now. Like, how does this help us? What does this information tell us? Well, we know that EIJA has to equal AEIJ. So all these terms have to be equal. And again, for this case, we use example for for EIJ for this specific EIJ, where I was 2 and J was 3, and we're looking at a 3 times 3 matrix. But these two things have to be the same. This is this one is EIJA, and the bottom one is AEIJ, and these two matrices have to be the same, which means this term has to equal this term, and again this term has to equal this term, and more importantly, this term has to equal this term. So A12 has to be 0. And again, we look at this term has to equal this term. So A31 has to be 0. And then we look at A32 and this term. So A32 has to be equal to 0. So we see that a lot of terms have to be 0. The only time they overlap is over here. This term has to equal this term. So A33 has to equal A22. And here we can see already our proof. We can see that A is going to be a matrix such that every single term will be 0. The only terms, every single term, yeah, will have to be 0. Again, we look at a through 2, well, a through 2 will have to equal this, so a through 2 will have to equal 0. So already, only with this combination, with this choice of ij, we already see that a through 1, a through 2, a1 2, and a through 2 all have to be 0. And we see that a through 3 will have to equal a to 2. And again, 3, 3, 2, 2, this is, these are diagonal entries. So a through 3, so these will all have to be 0, except for a through 3, which is here, and it will have to equal a to 2, and a bunch of other terms that we already see will have to be 0. And then again, we can multiply our matrix A by a different eij. We can multiply our matrix A then by an eij which has a 0 here, but it has like a 1 here, let's say. And then we're gonna get different information. Then we're gonna get that maybe a55 has to equal a66, and we're gonna get a bunch more terms which have to be 0. And that's how at the end we're gonna see, when we loop this for every k and I, when we loop this for every I and j, so when we multiply a by the matrix eij, where the 1 goes everywhere, we're gonna see exactly that a has to be a matrix with zeros everywhere, except the diagonals don't have to be e equals 0. The diagonals have to equal all the other diagonals. A to 3 will have to be equal to a to 2, a to 3 will have to be equal to a44, a44 will have to be equal to a66. We're going to see that all diagonals will have to be equal to each other, so all the diagonals could be 0, but they could also be any number. They could be 5, but then they all have to be equal to 5. So this is basically, that's the end of the video. That's kind of how we get to the end of the proof. But the geometric thing, if you just see by the geometry, some people might not be convinced, and you say, well, you can't, how do I formally prove this? So actually, once you get this information, once you know that, once you know what multiplying a by eij does, then if we actually want to formally do this is going to take like 5 more minutes, and it's way more harder to understand if you don't have the geometric intuition. But I'm gonna still do it just so just in case anyone wants to really formally prove this. So I'm gonna say that so how do we actually show that only aii and ajj terms have to be equal and all the other terms have to be 0? Well, we look at, okay, so I completely messed up, so I have to record this part again. But basically, the geometric intuition makes sense. But if anyone wants a more formal proof of why this actually holds, without just explaining that these with the drawings of these matrices, we can have a more formal proof by, first of all, by actually using the indices, making these indices count. So we get this over here, we have this information over here. So now we can look first, we can focus on this part over here, and we can focus on every specific index of this. So we have eij a k l. So we're looking at this, and we know that this will have to be equal to 0 for every k that doesn't equal I. Again, because why is that true? Well, we looked at eija. We looked at EA was over here, and we saw that this over here, only the ith row is going to survive. So basically, we showed that only the kth row is non-zero in this case. So in this case, for here k equals I, so only the kth row survives. So we know that this will equal to 0. We showed it before, for every k that doesn't equal to I. And again, because eij akl has to equal to a eijkl, because again, these two things have to be the same thing. So every term, for every index, every single index has to be the same. And well, because this holds for this guy over here, it also has to hold for this guy over here. So we get that a eijkl has to equal to 0 for every k that doesn't equal to I. And now what we're gonna do is we're gonna fix L equals J. So we're gonna say that L equals J. And why are we doing this again? Because this is a statement. And it has some information. And we're trying to squeeze some information out of this. And again, if L doesn't equal J, if L over here doesn't equal J, well then eij will always be 0. So I guess this term will always be 0. In our sum definition, and then this will always be 0. So there's no point. The only if you have any hope of this term having a non-zero entry, we know that L has to be equal to J, and then K also has to be equal to I. But we're gonna let K vary, and we're gonna fix L to be equal to J, so that we can even get some non-zero entries. And what we're gonna be looking at now is, so we fix this, and then we let k vary. So k can vary from 1 to n. And what we're gonna get now is that a e I j kj will equal to a ki, and that of course, as we said here, has to equal 0 for every k that doesn't equal I. So again, we have this over here that has to equal 0 for every k that doesn't equal I. We can fix L so it has to be equal to j, and if we do that, if we do this over here, we get that this has to equal aki, and this will equal 0 for every k that doesn't equal I. And again, and we can vary k from, k varies from 1 to n. Again, how exactly can we see that? Well, this this over here, this just equals this will just be equal to the sum. This will just be equal to the sum from m equals 1 to n of a km times e I j m j, and again we can see that this sum, again we fix L, we fix that j equals L, so j here will have to be equal to L, and so I can already replace this with L, and m can vary, but again this, so for each term n can vary. For every k, we start with k equals 1, n can still vary, but m, this term will be non-zero only for m equals I. So all of this for each term, for each k. So first we're looking at a1, for k1, the only time that in this sum we're gonna have a sum of n terms, but the only time this will be non-zero is when m equals I. The only time this will be 0, the only time this will be 1 is when m equals I. So only the only the aki term is going to survive. So we're going to get, a11 is going to survive, a1, so basically, what this will be equal to, ak always stays, so we'll have ak, but only when m equals I, the term is going to survive, and this will be 0 for every k that doesn't equal I. Again, it's really hard to explain. Like, the best is just for you to look at it yourself. The geometric picture makes the most sense, but you really have to think about the indices for a while for it to actually make sense. But basically, we get this out of this information over here, and again, we can do a similar thing with the opposite way. So we have a e I j k l, and I'm not gonna try to explain it too much, also because I really want to go to sleep and it's really late. But this will equal 0 for every L that doesn't equal j. Again, we showed that before. And then again, this also has to equal, if this is true for this guy, then also eij kl has to equal 0 for every L that doesn't equal j. And what is this actually equal to? Again, now we're gonna fix k equals I, so that k equals I, so that this index will actually be non-zero, so we can actually get some information out of this. Not 1. We're gonna fix k equals y, and k equals I, and we're gonna let L vary from 1 to n. We're gonna let L vary from 1 to n. What we're gonna get, again, for looking at this, is gonna be this will be the sum from m equals 1 to n of e I j I m a m l, and that would just be equal to ajl. And again, we said that this has to be equal to 0 for every L that doesn't equal j. So aj1 has to be 0. For this we get that aj1 has to be equal to 0, aj2 has to be 0, aj3 has to be 0. These are all terms of a, and they all have to be 0 for every L that doesn't equal to j. So only ajj doesn't have to be equal to 0. This is our grand revelation. And now what we also found out is that since a e I j has to equal to e I j a I j, they have to be equal. Well, this one over here, we just showed, we just showed that this one, for ij, it has to equal to aii, and the ij term has to be equal to ajj, so they have to be equal. And this is how you formally show it with indices, and it's so hard, to actually, like, it takes such a long time to grasp. It does actually make sense if you look at it long enough, and then it's really satisfying. But it's just really hard to explain, because each time I also look over it, I forget it, and then you have to look at it for like a few minutes and actually remember it. But if anyone's actually, if anyone actually wants to do this, it's hard to memorize. You just have to go by the logic of the indices, and it does make sense. It just takes a really long time, and this just shows you how powerful, a sketch can actually be, how powerful this can be, because it makes so much more sense. But yeah, that is the end of the proof. Basically, we can do this for every, we can do this for every I and j. So for every I and j, we can do this sort of analysis. So for every oh my goodness, this how does it even look? So for every I and j, we can make an eij and then multiply by a, and get this over here. So again, at the end, we're gonna see that a has to be such a matrix that all of these have to be equal. So we can just call them a. All of these have to be equal, and everything else has to be 0. This is the only a that is possible. I mean, it's a clean proof. Like it was very satisfying working with it when I was thinking about it. It just kind of almost the coolest part is at the start how we transform this problem into a problem that A has to commute with every single matrix P, and kind of how we also find such an invertible matrix, because we know this holds for every invertible matrix, but we find the specific invertible matrix, a very specific one, which looks like this, such that we're actually gonna at the end get this information over here, and then we actually see that with this we can squeeze a lot of information out of A. We have no idea what A is, but if we multiply it by a smart enough invertible matrix, we can get the information about every single term of A out of it. So it's a really smart choice, and we don't care about any other invertible matrix. The specific one, with this specific form, helps us squeeze all the information out of A that we need to fully define A. So yeah, thank you for watching, and that is all, and I hope it wasn't too confusing.